Hello, today we're going to focus on limiting reactants. Yesterday, or the day before, you worked on the gizmo that discussed limiting reactants, and you may have figured out some things, but I just want to make sure I get everything explained so everyone has the same ideas going into as we get ready to finish this unit. So limiting reactants are very simple. Typically what we've been looking at in the past with stoichiometry, you'll see something like, oh, you have 50 grams of reactant A, and the rest are in excess. How many grams of product do you make? So what a limiting reactant is just the one that's going to run out. So that's why we say everything else is in excess, so that you know that that's the one we want to focus on. Now with limiting, when we're now dealing with this, you're going to see questions where you'll have so many moles of reactant A and so many moles of reactant B. How many moles of product are you going to see? And we'll do that in a minute. So one of those is going to be limiting because one's going to be used up and run out during the reaction, and that essentially stops the reaction. The other is the excess reactant. That's the reactant that's left over at the end of the reactant. And we can, from all this data, we should be able to calculate how much is left over. So we're going to get some practice with that today. So let's think about this in a more simplistic terms that we can all kind of have common understanding of. So let's talk about the common s'more, our favorite campfire food. Toasted some graham crackers, piece of chocolate, and toasted marshmallow gives you a s'more. So if I have the chemical formula here for that as 2 graham crackers plus 1 chocolate square and plus 1 toasted marshmallow is going to give me a s'more. So hypothetically, you have 5 graham crackers, 3 pieces of chocolate, and 7 toasted marshmallows. How many s'mores can you actually make? What are those that are in excess? What are the ingredients that are in excess? So looking at this, we have 5 graham crackers. So if we're looking at this as a ratio, 5 divided by 2 gives me 2.5 s'mores. So from, if everything else was in excess, we can make 2.5 s'mores. Well, we really don't want to make a half s'more. So in all reality, we can make 2 s'mores from this. If chocolate was our limiting reactant, everything else was in excess, we can make 3 s'mores from the chocolate. And finally, if we look at our toasted marshmallow, based on this, if the other ingredients were in excess, we could make 7 s'mores. But we can only make 2 because we only have 5 graham crackers. So if we think about that, we can make 2 s'mores, which means everything else is going to be in excess. We're actually going to have 1 graham cracker left as well. We're going to have, if we make 2 s'mores, 3. So from every time every time we make a s'more, we're going to use 2, or we're going to use 1 chocolate. So if we make 2 times 1 is 2. 3 minus 2 gives me 1 extra chocolate. And the same here, we have, since we made 2 s'mores, we're going to use 2 toasted marshmallows. So that means we started with 7. 7 minus 2 gives me 5 toasted marshmallows in excess. So our excess is one chocolate square, 5 toasted marshmallows, and really we also have 1 excess graham cracker. So how does that work when we are thinking about chemistry? So let's look at this example here when we're looking at hydrogen plus oxygen gives me water. So we have right at the top, we have our balanced equation of 2 hydrogen plus an oxygen gives me 2 waters. So over here, looking at at this first one here, we can see we have 1, 2, 3, 4, 5, 6 molecules or moles of hydrogen. We have 1, 2, 3 moles of oxygen. So if we break these down separately, every time we use 6 moles of hydrogen, we're going to use, or every time we use 2 moles of hydrogen, we're going to use 1 mole of oxygen, producing 2 moles of water. So if I can kind of group those together, just to think of this visually, use 2 of those. Every time I'm going to use 1 of those. So if I'm going to use 1 2, 3, 1, 2, 3. Great. I have 3 that everything kind of balances out. We're going to use one of each. So again, if oxygen was in excess, I could make 6 moles of water. Everything was in excess. If we look at our molar ratio of 1 to 2, so every time we use 1 mole of oxygen, I'm going to make 2 moles of water. So 3 times 2 is going to give me 6 moles of H2O. So since they're the same, we're going to use up everything that we started with for each. We're going to end up with 6 moles of water with nothing left over. And the same thing looking at this one. We have at the next one below 1, 2, 3, 4, 5, 6, 7. We have 8 moles of hydrogen. 1, 2, 3, 4 moles of oxygen. Our hydrogen if we have 8 moles of hydrogen, we have a 2 to 2 relationship between the hydrogen and the water, which means we should be able to form 8 moles of water from that. Every time I use 1 mole of oxygen, I'm going to make 2 moles of water. So 4 times 2 gives me 8 moles of water for that. So I have nothing there. Since these are exactly the same, we know we're going to only make 8 moles of water. So let's look at these next 2 sets. So first, let's look at the hydrogen here. We have 1, 2, 3, 4, 5, 6 moles of hydrogen, which, if we're going to assume oxygen initially is going to be excess, will give us 6 moles of H2O. And I'll show you the math in a minute. 1, 2, 3, 4 moles of oxygen would end up giving us 8 moles of water. Well, we basically want to look at the one that makes the least amount. So right here, we're looking at 6 compared to 8. Well, 6 is lower than 8, so we know we're only going to make 6 moles of water. So if I'm going to do this visually, let's see, I'm going to use 1, 2, 1, 2. So every time I use one of these, I'm going to use one of these. Use one of that, I'm going to use one of these. Use that one. So I'm left over with 1 mole of oxygen is left over. So our limiting reactant is our H2 and our excess reaction is our O2. So think about this mathematically. If I'm making 6 moles of H2O, how many moles of water am I going to use? I would just do a molar ratio. 2 moles H2O, 1 mole of O2 means I end up 6 divided by 2 gives me, I'm going to use 3 moles of O2. I'm going to just put this used right here at the end. So if I started with 4, 4 minus 3 gives me 1 mole of O2 left. If we're looking at this next one down here, we have 2 moles of hydrogen, 1, 2, 3, 4 moles of oxygen. So in this case, the 2 moles of hydrogen, so 2 moles of H2, let's do a molar ratio. I'm just going to actually do the real math here. So for every time I'm going to do 2 moles of H2 gives me 2 moles of H2O, gives me 1 mole, or sorry, yeah, 2 moles. 2 moles of water. Looking at the oxygen, we have 4 moles of O2. And now we have a 2 to 1 ratio. So every time we're going to have 2 moles of H2O per 1 mole of O2. 4 times 2 gives me 8 moles of water. Well, 2 is less than 8, so we're going to go with that one down below. We're going to have 2 moles of H2O produced. If I'm producing 2 of those, but I could have made So if we think about this visually again, I'm going to have 2 of those. Every time I use one of those, I should have 3 moles of O2 left over. So our limiting reactant here is H2. And our excess again was O2. If we started with 4, if we were going to, since we only made 2, we have 2 moles of H2O actually produced. How many moles of oxygen are we actually going to use? Again, we use our molar ratio. 2 moles of H2O, 1 mole of oxygen. 2 divided by 2 gives me 1 mole of O2 used. And since we started with 4 minus 1 gives me 3 O2 left over. And you can see that the math and the visualization work the same. So now let's look at, what if I did this with we're using the same thing, but now I'm going to use grams of hydrogen and grams of oxygen. So if we're looking at again, I'm going to go ahead and put our formula here. H2 plus 1 O2 gives me 2 H2O. I have 50 grams, and this just makes my life a little easier by doing this. 50 grams of H2, 100 grams of O2, and we want to know how many grams of H2O would we have in the end. Well, to do this, we're going to do 2 stoichiometry problems and look for which one is going to make the least amount of product. So let's start here with our hydrogen. We have 50, and it would look like, hey, I have the least amount of grams of hydrogen, but we want to know moles. So if I have 50 grams of hydrogen, we need to get to moles of hydrogen, and then eventually moles of water. So to get from grams of hydrogen to moles of hydrogen, we're going to use molar mass. And since we have 2 hydrogens, we're going to say I'm just going to make it simple, 2 grams of H2 for every mole of H2. Now let's get to our switch so that gets rid of our grams of H2. So now we're going to go from moles of H2 to moles of H2O. So I'm going to have 2 moles of H2, 2 moles of H2O. Again, just our standard stoichiometry. And that's going to give me 50 divided by 2 times 2 divided by 2, which is just like 1. So we're going to have 25 moles of H2O. Now you notice I didn't go to grams yet because it's a lot, oftentimes it saves a step of not having to do this by just stopping here. So now let's compare. Now let's look at our oxygen. We have 100 grams of O2. And that's 16 grams per mole for each oxygen. We have 2 of those, so we're going to have 32 grams per 1 mole of O2. Okay, now we're going to go from, we've gotten rid of our grams, we're over to moles. Now let's go from moles of O2 to moles of H2O. All right, so we look at back at our balance equation. We have 2 moles of H2O for every 1 mole of H2O or of O2. So take 100 divided by 32 times 2 ends up with 6.25 moles of H2O. Well, looking at this, if we compare now we're going to compare these two with each other, and we can see that we're only going to make 6.25 moles of water because that's our lower number. Once we make those 6.25 moles of water, the reaction stops because we're out of oxygen. But we're still going to have some excess excess water, so excess hydrogen. So let's figure out how many grams, so we can answer our question, how many grams of water are we going to actually produce? So, because we're at moles now, so if I have 1 mole of H2O, and we have 18 grams, 16 plus 2 is 18 grams of H2O per mole of water. So this will cancel these out. So 6.25 times 18 gives me 112.5 grams of water. So if I have 50 grams of hydrogen and 100 grams of oxygen, that oxygen is my limiting reactant, and from that we'll make 112.5 grams of water. Now let's take this the next step. How much hydrogen do we have left over? So if I only made 6.25 moles of water, we can do is just do this and say, all right, I only made 6.25 moles of H2O, and this is why I stop at moles, because it makes doing excesses much easier, of water. All right, so how many moles of hydrogen we actually used? So again, this was 2 moles of H2, moles of H2O. So we actually used 6.25 moles of H2 use. Now convert that into grams. 2 grams of H2 per mole of H2 gives us 6.25 is 12.5 grams of H2 was used. We started with 50. We subtract out that 12.5. And we are left with 37.5 grams of H2 in excess. Simple enough? Well, let's go look at one more, a little more complex. Just go ahead and erase some of this so we can see easier. All right, we have the balance equation. Copper plus 2 silver nitrate gives me a copper nitrate. This should be, that's copper 2 nitrate, and 2 silvers. So according to the balance equation, we have how many atoms, okay? So I want to be real specific here. How many atoms, that's going to be my final answer. How many atoms of silver? That's what we're looking for, just looking at their word problem. We produce from combining 100 grams of copper and 200 grams of our silver nitrate. So again, let's do the stoichiometry for each, assuming one is the one that we're focused on is limiting and the other is in excess. So I have 100 grams of copper. So we want to get that into moles. So we have our molar mass of copper is 63.55. Oops, oh, I did that backwards. Hello, fix that. 63.55 grams of copper per mole of copper. We're going to get to silver. So moles of silver, moles of copper. Okay, it's a 1 to 2, so we have 2 moles of Ag. So every time we use 1 mole of copper, we're going to produce 2 moles of silver. So 100 divided by 63.55 times 2 gives me 3.15 moles of silver produced, if we're assuming that the silver nitrate's in excess. So now let's look at focusing in just on that silver nitrate. We have 200 grams of silver nitrate. Again, converting to molar mass, we need to do using molar mass to convert to moles. And in this case, it's 169.9 grams per mole. And we have a 2 to 2 molar ratio. So 2 moles of silver for 2 moles of our silver nitrate. So 200 divided by 169.9 times 2 divided by 2 gives me 1.18 moles of silver. So we now, so that we're at moles of silver, so we can see, comparing these two, we can see that our smaller one is 1.8, so that is our how many moles of silver we're going to produce, because at that point silver nitrate runs out and our copper is going to be left in excess. We're asking here how many atoms of silver are left over. Okay, so we want to go from moles to atoms. So in this case, we don't need molar mass. We're going to use Avogadro's number. 6.02 times 10 to the 23rd atoms of silver per mole of silver. So we take that 1.18 times 6.02 times 10 to the 23rd, and we end up with 7.1 times 10 to the 23rd atoms of silver. So I hope that kind of helps explain what's going on, how this was all figured out. Do some more practice. We're going to do some more practice again in our next lessons before introducing our last concept. So I hope that helps. Again, if you have any questions, feel free to call me or contact me, and we can go over this face to face. Thanks so much. Bye.